everyone. In this session, now onwards, we'll be studying soil hydraulics. It's a big chapter with a lot of material in it. So this is module number 3. Soil hydraulics is the common title for it. There are many things involved into that. We'll see the syllabus first. So module 3 consists of 3 major parts, as you see here: flow through soils, seepage analysis, and then effective stress analysis or principle. Right, under flow through soils you've got Darcy's law, coefficient of permeability and its determination in laboratory and field, factors affecting permeability, permeability of stratified soils, seepage velocity, superficial velocity, and coefficient of percolation, capillary phenomena. All this is in flow through soils. Under seepage analysis, there is a mathematical approach to analyze flow through soils. It is Laplace equation proof, assumptions and limitations in its derivation, flow nets, characteristics and applications, flow nets for sheet piles and below the dam section, unconfined flow phreatic line using Casagrand's method with and without tow filter, flow through dams, design of dam filters. Okay, Terzaghi gives filter design, that one. So effective stress analysis, you got what is the meaning of geostatic stress, effective stress concept and total stress, neutral stress and impact of the effective stress in construction of structures, quicksand phenomenon. These are the things which are to be covered in module number 3. We'll be covering in detail one by one. Okay, why to study soil hydraulics? What are the applications? Necessity of study of soil hydraulics is to estimate the groundwater flow towards wells and to assess uplift pressure under hydraulic structures and to calculate seepage through earthen dams, to judge the rate of settlement of saturated clay soils. Okay, modes of occurrence of water in soil. There are 2 types of waters that will be existing in the soil. One is called free water, another one is called held water. Free water, which is sensitive for gravitational force. Gravitational water, it is also called as, present in saturated soils with the top free water table moving up or down depending upon the water is sucked out or recharged. Held water, the water present in soil which does not move because of force of gravity, is structural water, adsorbed water and capillary water. Okay. Now that there is a term called permeability. It is ability of the soil to permeate the water through, is nothing but permeability. Since water can flow through the pore spaces in soil, the soil medium is considered to be permeable, right? Because there are interconnected voids. Through these voids, obviously water can seep through. Thus, the property of the porous medium, such as soil, by virtue of which water can flow through it, is called permeability. In other words, the ease with which the water can flow through a soil mass is termed as permeability. Now, there is in this connection the most important starting idea or concept that you are going to learn would be Darcy's law, and most of the things now onwards will be depending upon this simple law, which is given by mathematical equation V is equal to Ki. Now what is the theory? We'll see. Darcy's law. Thus the theory of seepage flow in porous media is based on generalization of Darcy's law, which is stated as, what is Darcy's law? It is velocity of flow in porous soil media is proportional to the hydraulic gradient. Velocity of the flow through porous media is proportional to hydraulic gradient. So if you just put this equation itself, V is proportional to hydraulic gradient is represented as I. V is proportional to I. Now if you convert this equation into this proportionality expression into equation, it will be V equal to Ki, where K is proportionality constant. Flow is assumed to be laminar, so that is V is proportional to I. Now V is equal to Ki, where K is the coefficient of permeability, V is the velocity of the flow, and I is the hydraulic gradient. That is the Darcy's law. Alright, very simple but very powerful tool to use calculation of flow through soils. What are the assumptions made in Darcy's law? First one, the flow is laminar, that is fluids is described as a laminar if fluid particles flow follows a definite path and does not cross the path of other particles, that is to say laminar flow. Okay. Now water and soils are incompressible, that is continuity equation is assumed to be valid. Number 3, the soil is saturated, no voids are left with unfilled gaps or voids, that is no void is occupied by air. Everywhere there is a water, because of that it can flow through, that is what the point is. The flow is in steady state, that is flow condition do not change with time. Flow condition do not change with time, and it is steady. Okay, validity or limitation of Darcy's law. This is an important thing. Darcy's law, in its mathematical form, it is V equal to Ki, is true for laminar flow through the white spaces. A criterion for investigating the range can be furnished by Reynolds number, because whether it is laminar or turbulent is decided by, we know that it is decided by Reynolds number. Flow through soils, Reynolds number Rn can be given by Reynolds number for the flow through soil is given by Vd rho by mu. Similar expression, but the major idea is what is d here, right? So where V is discharge or superficial velocity in centimeter per second, so discharge velocity or superficial velocity, d is the average diameter of the soil particles in centimeters. Density of fluid in grams per centimeter cube. Mu, the coefficient of viscosity, is in grams per centimeter second. So everywhere they have used grams and second and centimeter. Right? Mass is in grams, length is in centimeter, time is in seconds, so that everything cancels off. You'll be left with plain number. Right? For laminar flow conditions in soil, experimental results show that Rn is less than or equal to 1. So in soils, the value of Rn comes out to be less than or equal to 1. With coarse sand, if you say, assuming d is equal to 0.47 mm, K is equal to 100 d squared, so 0.2209 centimeter per second is the velocity, because K is nothing but velocity under unit hydraulic gradient. Assuming I equal to 1, then V is equal to Ki, 0.2209 centimeter per second. Also, water is 1 gram per centimeter square, and mu at 20 degrees centigrade is around 10 minus 10 to 5, 980 grams per centimeter square. This, if you substitute and Rn is calculated, roughly it comes out to be 1.059, or it's approximately equal to 1. This is for coarse sand where the flow will be turbulent. Now if it becomes smaller, the velocity becomes lesser, and because of that this comes out to be less than 1. So from the above calculations we can conclude that for flow of water through all types of soil, sand, silt and clay, the flow is laminar and Darcy's law is valid. With coarse sand, gravels and boulders, turbulent flow of water can be expected. So sand, silt, clay, it is laminar flow only. If it gets coarser with coarse sand, gravel and boulder, the Rn becomes more than 1, so indicating that there will be turbulent flow. Okay, so that is limitation of Darcy's law. Okay, here seepage velocity and superficial velocity, there are two velocities. One has to understand this. Okay, now consider flow of water through soil medium of length L here, and cross-sectional area. So here cross-sectional area may be circular generally, maybe any other shape, but cross-sectional area, if you cut it, the cross-sectional area is A, right? If V is the velocity of a downward movement of the drop of water from position 1 to 2, then velocity is equal to Ki. Therefore K can be interpreted as approach velocity or superficial velocity for a unit hydraulic gradient. V is equal to Q by A. So when it is moving 1 to 2, means this velocity, right, approach velocity or superficial velocity for a unit hydraulic gradient, V is equal to Q by A. Now drop of water flows from position 3 to 4 at a faster rate than it does from position 1 to 2. 1 to 2 it moves slower, 3 to 4 it moves faster, because the discharge has to be same, but here cross-sectional area is full, but in this case cross-sectional area through which the water is flowing is less, because there are voids. Only through the voids the water has to pass through. So it is not full area through which the flow is occurring. Because of that, when cross-sectional area reduces, the velocity has to increase. That's why from point 3 to point 4 it will be having much faster velocity, and the actual velocity of flow through the voids is termed as seepage velocity, Vs, which is discharge divided by AV, that is volume of voids. Discharge divided by whole cross-sectional area. If we take the full cross-sectional area, then it will be superficial velocity. Actual velocity is seepage velocity. That is the difference. Okay, seepage velocity is actual velocity. Superficial velocity is what is known as apparent velocity, right? Okay, so if you can see that the flow from point 1 to 2 it is slower, and then from 3 to 4 it will be faster. Okay, one more way of putting the same thing, seepage velocity and superficial velocity. Now you just see the discharge which is coming from top through the soil and then coming out. This is, let us say, 20 centimeter cube per second, let us say, and cross-sectional area, the total cross-sectional area is say 10 centimeters square. Then the velocity of the flow from 1 to 2 becomes 2 centimeters per second. But velocity of seepage will be depending upon area of voids through which the water is flowing. So same quantity 20 centimeter cube per second, but passing through only voids. The voids area is 5 centimeters square. So what happens now? The velocity becomes faster. That is from 3 to 4 it will be faster. That is the actual velocity through the pores. So that is 4 centimeters square, 4 centimeter per second. The earlier one will be referred to as seepage velocity, superficial velocity. This is seepage velocity. Okay. Okay. You can just see that it is slower when it moves. Right? When it moves here, it will be only through the pores and it will be faster. Okay. By the principle of continuity, the velocity of approach V may be related to seepage velocity or average effective velocity of flow, which is Vs, by equating discharge which is going in should be equal to discharge which is going out, A into E equal to AV into Vs. Okay, now this V will be AV Vs divided by A, that is volume of voids divided by A. Right, volume of voids is nothing but area of voids multiplied by length L, and this area multiplied by L is nothing but total volume. So from this what I have done is I have multiplied by L divided by L, keeping all other terms same. Okay, here Vs has to be suffix S, AV, V has to be suffix V. Anyway, area of voids multiplied by L gives you volume of voids. Area of cross-sectional area, total area multiplied by L gives you total volume. But VV, volume of voids divided by total volume, is nothing but porosity. Hence, relation between V and Vs becomes V is equal to N into Vs. That is, apparent velocity or superficial velocity is equal to N times actual velocity or seepage velocity. Now this is V equal to Ki. Now Vs becomes K divided by N into I. This K divided by N itself will be known as Kp, which is coefficient of percolation, whereas K is called coefficient of permeability, where AV is area of pores, V is total volume of soil, VV is volume of voids, E is voids ratio, N is porosity. With all that notations, K is coefficient of permeability. Above equation indicates that seepage velocity is also proportional to hydraulic gradient. Seepage velocity proportional to hydraulic gradient. That proportionality coefficient here, Kp is called coefficient of percolation, gives Kp is equal to K by N. Thus, coefficient of percolation is defined as the ratio of coefficient of permeability to porosity. Okay. Now, factors affecting permeability. The relationship showing dependency of soil permeability on various characteristic parameters of soil and permeant, that is the fluid which is flowing through it is permeant, was developed by Taylor as given below. So this is an important equation for remembering factors affecting permeability. K equal to D squared gamma by mu. D is the size, effective size of the soil particles, effective size in the sense D10 it is. Then if you look at gamma by mu, these are permeant characteristics. So gamma is the unit weight of fluid, mu is the viscosity of the fluid. Then the C is the shape factor, and E cube divided by 1 plus E depends upon the arrangement of soil particles. Therefore, factors affecting permeability can be listed If you remember this equation, it depends upon viscosity of the permeant, depends upon density and concentration of the permeant, grain size, this one D, White's ratio, the E, composition, how it is arranged, soil structure, degree of saturation, then presence of entrapped air and other foreign matters. That's how permeability depends upon. Capillary water in soils. What is this? Capillary rise results from combined actions of surface tension and intermolecular forces between the liquid and solids, which is known as adhesion. Right? The rise of water in soils above the groundwater table is analogous to the rise of water into capillary tubes placed in a source of water, but the wide spaces in soils are irregular in shape and size as they interconnect in all directions. So voids are of different shape and size. The pressure on the water table level is zero. Any water above this level must have negative pressure. In soils, a negative pore pressure increases the effective stress and varies with the degree of saturation. Okay, thank you. Let's stop here.